In example 4, we have a spherical tank with a radius of 8 feet, half full of oil. They give us the weight of the oil for each cubic foot. We want to know how much work is it going to take to pump all of the oil out through a hole in the top of the tank. We remember that work is equal to force times distance, generally speaking. We think of force as weight. So we're going to be talking about the weight of this oil. So to help us set this up, I'm going to first sketch a picture. So I have a circle here that I'm going to center at 0, 8. And I'm going to give it a radius of 8. So I have this circle this sphere sitting on the top half of the XY. It's half full of oil. So from here down, we have oil in this sphere. We're going to think of the oil as being cut into slices. So I'm going to come in and take a slice of this oil, a cylindrical slice like this. So I have a slice of oil with a thickness of what I'll call delta Y. I slice it because the weight of each slice is going to be different. So we're going to focus on the work of just one slice, which is equal to the force of the slice times the distance that the slice has to travel as it gets pumped out the top of the tank. Now the force of the slice is the exact same thing as the weight of the slice. And once we have this expression, we'll integrate it over all of our slices. So first, let's talk about the weight of the slice. Well, they tell us that the oil weighs 50 pounds per cubic foot. 50 pounds per cubic foot. Cubic foot is a measure of volume. So 50 pounds per 1 unit of volume. Well, what's the volume of our slice? Our slice is a cylinder, and the volume of a cylinder is pi r squared h. So the volume of that slice is pi r squared. R, the radius of this slice, I'm just going to call x. And I'm calling it x because the radius would be different if I had taken the slice to be up here. It would be larger. So I'm just going to call the radius of that particular slice x. So we have pi r squared, that's x squared, h. How tall is the slice? Well, the slice is delta y units tall. So we have an expression here for the weight of the slice. The problem is that I see this delta y, which means I know I'm going to be integrating in terms of y, but I have this x squared in my expression, and I'm going to need everything in the integral to be written in terms of y. So we're now going to have to find a way to rewrite x squared in terms of y, and we do that using the equation of this circle. So what I have here is a circle with a center at 0, 8 and a radius of 8. That means the equation of that circle is x squared plus y minus 8 squared is equal to the radius squared, which is 64. This is going back to simply the equations of circles. So I can conclude that x squared is equal to 64 minus y minus 8 squared. And I'll use that instead of x squared when I go to write the weight of the slice. So we now have an expression for the weight of the slice. The weight of the slice is 50 pi. We got the 50, the pi. I'm not writing x squared. Instead of x squared, I'm writing the 64 minus y minus 8 squared, which is the same thing as when we expand that out, negative y squared plus 16y. I encourage you to go through that algebra. And we still have the delta y on the end. So all of this here is just our expression for the weight of the slice. Now we have to go find how far does the slice travel? What's the distance that that slice travels? Well, this red slice has to make it all the way out the top of this sphere. I do know that the top of the sphere is at 16 because the radius of the sphere was 8. Now, what distance is at the bottom here? What's this distance down here that this did not travel? Well, that's simply y. That's simply y in the equation of the circle that we wrote. X squared plus y minus 8 squared is equal to 64. So if the slice is y units off of the x-axis, and it's 16 all the way at the top of the sphere, then that gray distance that the slice is actually traveling is simply 16 minus y. So for the distance of the slice, we have 16 minus y. Now, all of this is just the work for one slice. We're going to need to integrate over all of the slices. First, I'll just do some algebra to simplify what we have in here. So this is what we get from just expanding and combining like terms. There's a lot of algebra in here that I'm not going through, but I encourage you to take some time and actually multiply all this out. So really I'm taking this and I'm foiling it with that to get this expression right here. I just kicked my delta y out to the end. Now I'm ready to start to set up my integral. So work is going to be the integral of all of this. The delta y on the end will turn into a dy when we change it to an integral. And now we need to think about what our limits of integration are. We are integrating with respect to y, and we said that y, the same y in the picture that I have marked in purple, is the distance from the distance of the oil from the bottom. The distance of the oil from the bottom. Well, the distance of the oil from the bottom, what values could that range over? Well, there is oil at the bottom of the tank. Well, that has a distance of 0 from the bottom. And then there's oil, remember the tank is half full, up to the middle of the tank. Well, that has the distance of 8 from the bottom. So we are integrating from 0 to 8. Again, I want to pause here for a second because everything that we've talked about so far is from this section. At this point, once we have this integral set up, we're just doing a regular integrating using power rule and applying the fundamental theorem of calculus. So I'll go ahead and integrate this. We can think of the 50 pi as a constant that we don't have to regard. We'll increase our exponent by 1 and divide by our new exponent. And then we will apply the fundamental theorem of calculus. To get our final answer, remember we were working with feet and pounds. So our final answer of work will be measured in foot-pounds. 589,782 foot-pounds. In this problem, we have a space module that weighs 15 tons on the surface of the Earth. We want to know how much work is done in propelling the module to a height of 800 miles above the Earth. So it's moving in this direction, and it's going to land about there. We are given that 4,000 miles is the radius of the Earth, so I'll label that in the picture, and we're not going to consider air resistance or the weight of the propellant. So what we need to do is we need to calculate the work, which we know is the integral from A to B, force times distance. So what we want to find is this force function, and we'll also need to know the distance that that propellant is traveling. So for the force function, we will be using Newton's law of universal gravitation. So the law gives us a formula for the force function if we are given distance in meters and force in newtons. But there's a comment down here where if it's not known that the force is measured in newtons and we do not know the masses, then we can assume that F is equal to C divided by D squared. And for our purposes, we'll use this version. Notice that we do not know what C is. It is some constant. because at the end of the day, what the law says is that the force is proportional to the product of the masses and inversely proportional to the square of the distance between the two particles. So that's why we have d squared in the denominator. This proportionality constant g is only if we are given newtons and meters. We don't know what it is, so we call all of this right here some constant c and get to this formula there, and that's the version that we'll be using. So we have that f of x is equal to c over d squared. I'm going to say x squared, so I'm letting x equal the distance from the propellant to the earth, right? But when we measure distance from the earth and we're considering force, we take distance from the center of the earth. So we're talking about the distance from the center of the earth to the space module. And that's why we're given the information about a radius of 4,000 miles. So we do have some information in the problem that will help us calculate. See, we're given that the space module weighs 15 tons on the surface of the Earth. When we think about weight, remember that weight is a force when we're talking about gravity. So I can plug into this equation. I know that the force is 15 tons. I don't know what c is, but I know that it's on the surface of the Earth. Well, on the surface of the Earth, when the propellant is right here, what is the distance from the center of the Earth to the space module? Well, it's the radius of the Earth. It is 4,000 miles. So we'll plug that in and square. So now we can use this equation to calculate c and conclude that c is equal to the product of 15 and 4,000 squared. I'm not actually going to calculate that. I'll just leave that as that. But what we do know now is that the force function, the same function we want there, is c, which is 15 multiplied by 4,000 squared divided by x squared. Because notice that x is going to change as the space module begins to ascend into space. So now we need to talk about our limits of integration a to b. I just said that the x value is going to change. So what is the x value changing from? Well, it starts here on the surface of the Earth, where the distance from the space module to the center of the Earth is 4,000. So that is our lower limit of integration. And the ultimate place where it stops is up here, where it is 8,000 miles above the surface of the Earth. So that distance would be 4,800 because we have to add in the radius of the Earth. So those are our limits of integration. I'm going to go ahead and put our function that we found earlier in. And now we're ready to integrate. At this point, I'm going to pause because we've reached the point again where we started off with an application problem. We used some new concepts. So we introduced Newton's universal law of gravitation and applied it to find the work done to propel this space module into space. But at this point, once we have set up this integral, this is now a Calculus 1 problem where we simply need to use the power rule and the fundamental theorem of calculus to integrate this. So really emphasizing that this section and really this entire chapter is all about, can you apply new concepts to set up integrals that you already know how to integrate? In our next example, we consider a piston of radius r and a cylindrical casing. There's gas inside, and as the gas expands, that piston is moving, so eventually the piston would be back here, and all of this would be gas, and so on and so forth. We are given that the work to move the piston is given by this integral here. Notice that this integral is with respect to v, volume. So as the volume changes from some initial volume to a new volume, we need to integrate the function kv. K is some constant. You'll notice a theme in this lesson between these work integrals, that we're usually integrating some constant, and then there's a variable. It might be squared, it might be in the denominator. For instance, here we're integrating kv. In the previous problem, we were integrating c over x squared. So this is like a k, some constant value. In the problem for Hooke's law, we are integrating kx. That's it. So a lot of this lesson, these applications, is being able to know what these force functions are. So ultimately, in example 6, we want to integrate from initial volume to v1, k divided by v dv. To do that, I need to find k. So let's go do some algebra on the side to find k. Now, usually when we're finding k, there's some information that they've already given us. This is coming from this formula here, that P is equal to kV. P represents the pressure, V is the volume. So there should be some information in the problem that tells us what is the pressure and the volume at some time. So when we read this, the first sentence, a quantity of gas with an initial volume of 1 cubic foot and a pressure of 500 pounds per square foot expands. So we know that the volume, 1 cubic foot, pressure, 500 pounds per square foot. That implies, using the formula P is equal to K divided by V, that 500 is equal to K over 1, which tells us that K is 500, because I plugged in 1 for the volume. So now I'm going to take this K value and we're going to put that into our work integral. Now let's talk about our limits. Limits are what the volume changed from. We started with an initial volume of 1 cubic foot. That's our lower limit, and it expands to a volume of 2 cubic feet. So now we have an integral that, again, simply requires Calc 1 integration techniques and the fundamental theorem of calculus, and we'll have our answer. We're getting 500 natural log of 2, which is approximately 346.6, and this is foot-pounds.